about speed in Sage, Python, etc. So I made 3 separate worksheets. One is a extremely brief introduction to Python. The second is going to talk about a little question I threw out last time, which is there a closed form formula for sum of sine of 1 plus sine of 2 plus sine of 3 plus sine of 4, etc.? And if so, what does that give you? And then finally, I'll talk about something called fast float, which is another way of optimizing certain sorts of calculations. So again, the general theme this week is you have some code, maybe in Sage or some other math software, but specifically in Sage for this week, and you run it, and you're kind of maybe frustrated that it's sort of slow, and you wonder if it could be made faster. So I'm throwing out a lot of tricks and ideas. The third one, by the way, with fast float, what happened was on Monday, right after teaching this class, I went over to the math department, and Doug Lind, who's a professor over there, told me about some numerical integration stuff he was doing with Sage Math Cloud. And he said he wondered whether there was a way to make it faster. And I said, send me a copy of what you're doing, and I'll look at it. And I was able to speed up his computation by a factor of almost 600 with just typing 9 or 10 more characters around what he had. So I'll show you how that works. That's the last thing today. Okay, so first let's start with Python. So basically, I'm just going to tell you a little bit about the project, show you an easy example and a complex example that illustrate how Python works. And that's it. So first, the Python website. Oh, actually, so just some quick history. When I was looking at a whole bunch of programming languages back in 2004 in which to implement Sage, I wanted something where it was pretty easy to read and write the code for the implementation, but at the same time, a kind of key requirement is that it was possible to write code that was as fast as Magma. Magma being a computer algebra system that's mostly written in C. And so I had little benchmark programs that I would try out, and I would try implementing them in different languages like Python and OCaml and Lisp and all kinds of languages, and then just see how fast I could make them. And if trying as hard as I could, implementing these little programs still was 5 or 10 times slower than C, it was completely a non-starter because I'm doing research and I need things to not suddenly be 10 times slower. And nobody else would use the system who is currently using Magma if it's 10 times slower than Magma. So I looked at a lot of the languages, and even if they were super fast, they still weren't nearly as fast as C. C is just really, really fast. If you get down and dirty, you can make things really, really fast in C. And then I was flying home from Europe, and I had downloaded the Python C API reference manual and read it, which is kind of a funny thing to do. But if you really, really are into Python, it's like the Python as a program is also a C program with a C API. And you can call all the functions that implement Python just directly from C. It's a very powerful technique. And so I realized using that, you can write code, not surprisingly, for Python that you can use from Python that is exactly as fast as C. You simply write it in C and make it available in the Python interpreter. In fact, that's how an enormous amount of Python itself is implemented. You just, if they're going to implement a function to compute sine, like math.sine, remember we saw that? Really, it's just a few lines of C code. If you look in the implementation of Python itself, there's a few lines of C code to implement sine, just calling out to the standard library, and then a little bit of boilerplate to make it usable from the Python interpreter. And so you can write stuff that you can use from Python that's really fast. But I looked at it, I was like, okay, at least it's possible. But it's extremely scary and tedious because you have to do all kinds of manual reference counting. So it's really, really easy to leak memory and segfault and make all kinds of really bad mistakes in implementing Python via C extensions. So I started planning to write something that would automatically create these C extensions. And then when I got home off the airplane and had internet again, I searched around and it turned out there's something called Pyrex, which is a kind of a bad name because it's also the name of all those glass Tupperware things and stuff. So it's hard to search and so on. But it stood for Python extensions and Rex for some reason. But I don't know what the R is for. But it wasn't It's an amazing project. What it does is it lets you write Python code, and then you just put in a little bit of C annotations. There's like a slight extension to the Python language. It takes the Python code and turns it into C code. And if you write it just right, it's almost a one-to-one mapping from Python to C. And so the speed actually is exactly the same as C if you write the code correctly. Basically, if you use C idioms. But unfortunately, this Pyrex project, there's a guy, Greg Ewing, and he would basically work on it, as far as I could tell, like once a year around Christmas. And he'd do a whole bunch of work. And he didn't use a revision control system or anything. His revision control system was to make a zip archive every once in a while. And so it was kind of really hard. And there started to be little forks of it. And there were a ton of features of Python that weren't available, like list comprehensions. Those are nice, right? But you couldn't do them in Pyrex. So it was really like a really restricted subset of Python. So that was frustrating. And so I started adding little things to it and kind of making my own little fork, and other people were doing that. And then one of my grad students, Robert Bradshaw, started adding things as well. And I found this, I just happened to read this nice book called ProducingOSS.com, which if you're interested in open source software, it's an extremely good book. It's basically how to run a free software project. And since I had been running Sage, which was a big free software project, I was curious what they said. And I agree with almost everything in the book, and the things I didn't agree with, I complained to them, and they changed little things. They were against giving credit to individuals directly, which in academia is sort of a natural thing to do, but maybe not in companies. In any case, I decided that this Pyrex thing really, it would be better if instead of just this one guy working on it once a year, if it was more like a standard open source project. So right after I read this book, I'm like, all we need is a good name and somebody to lead the project. So I didn't want to do either. So I came up with so me and this undergrad, Tom Boothby, came up with a terrible name, and then I kept running it. It was called Sage X. This was before SpaceX and all the Elon Musk stuff. So maybe Sage X sounds good now, but it sounded terrible then. It's really hard to say. People didn't like it, and it didn't really go anywhere. So then a little while later, I decided I like compiler type stuff, but I don't know. It's really not my thing at all. I don't like writing programming languages, which is, by the way, why Sage just uses Python as its programming language rather than its own custom language like all the other math software. It's basically because I suck at and don't like writing programming languages. I'm way too lazy. It's just way faster to start with an existing one rather than making your own. So I came up with a good name, which was Cython. For whatever reason, it's a much better name than Sage X. And basically when I came up with it, I Googled it. That's not fair. So I Googled it, and there was almost nothing. Let's see. You can see, it's pretty much, there's some graphics, and most of the Cython stuff is now the programming language. All there was at the time, though, was this guy. His name is, or his punk rock name is Cython. And I figured he wouldn't try to, get the domain from me, so I got the domain and started the project, and then I found people who I thought should lead the project, and I asked them, could you lead this project? And they said, no, absolutely not. So I took multiple people who wouldn't lead the project, combined them together into one group of people that would. And it worked. So over the years, they've done a huge amount on it. It's actually extremely popular in kind of scientific Python. I went to a conference once in Europe on scientific Python, and half the talks mentioned Cython to some extent. So I was really amazed by that. So it's really an important project, I think, and useful. So let's see how to use it in Sage Math Cloud. But just to emphasize, this is something that's completely separate from Sage. You can use it in Python anywhere. And basically what you do is, instead of writing a .py file, which is how you make Sage code, or Python code, you make a .pyx file. And then you run the Cython compiler on that. And then it turns it into C code, and then that gets included in, or compiled and then included into some program or used from Python. So a lot of Python libraries that you install in some way, it turns out part of them are written using Cython and you don't even know. It's just kind of used behind the scenes. But Okay, so remember this, the sine sum thing that we did before. So let's see how long it takes right now. So remember, it's taking like 2 to 4 seconds depending on load. So that thing takes 2 milliseconds to evaluate. That was when we had sped things up, and the change was instead of just sine with the math.sine. So it went from about 4 to 5 seconds down to 2 milliseconds. You had your hand up first.
What is best of 3 refer to?
So what it does is it just tries timing it a bunch of times, and then does it again, and then does it again, and then takes the best of the 3.
Oh.
So it's like the fastest evaluation. And I think it takes, let's see, I wanted to put that as a homework assignment, but I forgot. Have you read the documentation? Because there's a page in the Python manual which is about defining this, and they argue that you might think you should come up with a distribution of timings and look at the mean and standard deviation, but that's actually very misleading because really the fastest time is the one time that matters. I don't know if I agree with that, but whatever. Yes?
How similar are Python and Python? Because on the whole, we're has to like compare like multiple coding languages.
Yes. Python is a different programming language. It almost has Python as a subset, but probably like that's one of the goals of the project. It might be very close. I'm not sure if it is now, but there are a huge number of things that Pyrex couldn't do that you could do in Python, like define a function, then inside of that function define another function, just like nested functions. It's a very useful thing to be able to do, but you couldn't do that in Pyrex. And then Craig Citro and Robert Bradshaw, they both spent a lot of time implementing that in Python, which is tricky because you have to kind of bake everything in C, where you can't have nested functions in C. And so there's lots of subtle stuff like that Python now does. I'm not sure if it has 100% of Python or not, but it's definitely not, I mean, it's a different programming language. It's like a superset. There are things you can write in Python that are not valid in Python, as you'll see shortly. I'm about to, well, here's some Python at the bottom. Okay, so let's see if we can make this a little bit faster using Python, okay? And we'll get a little bit. Here is some Python code. It's actually identical to the corresponding Python code at the top. I did nothing at all. I changed nothing except I explicitly had import math. What this does, if you put %Python at the top of the block, it will take the code that's there, which should be Python code, and compile it, and then any functions that you define there, it will make them available so you can call them elsewhere. Okay? So instead of having to like learn how to run the Python compiler and import stuff, you can just use it this way. And see, it defines sine sum Python 0, so let me try running this. There's some overhead, though. It takes a little while because behind the scenes, it created a C program, compiled the C program, and then loaded that into the running Python session. I'll click on auto-generated code in a moment. But as you can see, this will be slightly faster. So this right now changes a little from one moment to another, but it's on the order of like 20 to 40% faster. And this is actually typically what you see if you take just a random Python program and then compile it using Python and make no changes whatever to the program. You'll get typically a 20 to 40% speed up. That's roughly what happens. So it's not a huge speed up at all. And it depends. Sometimes things get a little slower. Sometimes they get dramatically faster, but usually it's about 20 to 30%. So here where it says auto-generated code, if you click on that, then it will pop up another page. And this is, I think, very, very interesting. What this does, this is a C program. This is the Python code with a little bit of extra imports at the top. And when you click on a line, it tells you what the corresponding C code is. And it's pretty big. There's a lot of overhead involved. But this code in yellow that you can see here, this is C code. And that one single line at the top gets converted into all of this C code. So we'll do a little more with this in a second in a another example where it's more useful to look at that. Oh my God, what just happened? Oh, because I zoomed in on the same page in the other tab, sorry. Okay, so this is another Python program that does pretty much the same thing, but there's a couple of differences. I've explicitly declared the types of all of the variables. And instead of using sum, I made a for loop. And I also said that instead of sign being math.sign, which is a Python function, which happens to be under the hood implemented using C, I want Python to directly use the sign function from the math.h, like from the C library, directly. And so here's the new code I wrote. All these sort of constructions are meant to look a lot like Python, but they're not Python. So cdef extern from, that lets you declare that that whenever you write, say, this function, it should use the one that's defined in math.h, and you should view it as having this signature. And then here you define a Python function, but it takes as input a variable m, which will get turned into a C int. And then the next line, this says that s is a C double, and that k is a C int. And then it makes this for loop. It looks like a Python for loop, but as we'll see in a moment when I show you the thing that was yellow before, this gets converted directly into a C for loop. By the way, this was yet another thing that Pyrex didn't have that we added, which was that it used to be you had to use some really funny syntax for loops, and if you did this, it would just be really slow. But it automatically converts this into the right thing. And then calls sign. So let's compile this one. And again, it should take like 1 or 2 seconds to compile. And then once it's compiled it, there's this auto-generated code. So let's go over here. If we click on one of these lines, again, I'll zoom in so it's easier to see. Wow. The servers are dying. If we click on one of these lines, we can see the corresponding C code that's generated. The fact that these lines aren't yellow tells us that there's a pretty simple mapping from Python to C, or from Python to C. So I'll click on, say, line 12. Oh, there's nothing there. Line 13. So this is the corresponding C code. It's just a C for loop. There's some funny variable names that it uses in C, but this is what it converts to. And the next line involving sign, it's just that. So, and the next line's a little more complicated. It has to turn S, which is a C double, back into a Python float. And it does that with the function pyfloat from double. Okay? So, if you have some Python code, which could be viewed as just a bunch of for loops and arithmetic involving C-level data types, which are, of course, very similar to Java data types, then using Python, you can convert that code into something that really is just C-level code and will run exactly at the same speed as C. Okay, and now let's switch back and run this. Okay, and now this will, in fact, be significantly faster. So it's looks like under around 472 microseconds versus, so the original one is 2 milliseconds. So the speed up over the original one, it's on the order of a factor of 5 in this case, 4 to 5. And that 4 to 5 factor, it's all overhead going between using basically math.sign versus just directly calling the sign function. I mean, it does take some work to compute sign. Okay, so that is an example of Python. There's a lot of other things you can do with Python, like make cdef classes. So you can define classes, but where they have functions that have C data types in them and take C objects as input and so on. Yes?
So is the difference between this one and the first Python function that you wrote, just this one uses the math.h form of sign?
There's two differences. One of them is that it uses the math.h form of sign, so it directly calls the sign function in the C standard library, rather than, remember that huge pile of like long Python C API conversions and stuff? That was what it did before. So that's one thing, but the second difference is that I've explicitly declared some data types here and used a for loop rather than just using Python's built-in sum. So there are two differences. Yes?
Is the for loop faster just because it's Python, or would the for loop be faster if you're doing this in pure Python?
I don't know. I doubt it would be faster in pure Python. It'd probably be exactly the same in pure Python. Yes?
Does the overhead of the extra code that you add when you convert to C, have you seen a significant difference between that versus just writing the same code in C on its own?
It's literally like the speed is exactly the same as if you wrote the code directly in C. So there's no difference. But let's say there's some subtle issue in here and you want to put in a print statement or something. It's really, really easy to do that in Python. You just say print blah, like you would do in Python. Whereas if you actually were to write this code in C, it would be painful to do that because you're manipulating potentially, well, you have to use printf. Okay, that's a little annoying. But it gets more complicated if you're working with more complicated objects. So it's often much easier to debug. And so you have like all this stuff in that's written in Python, and you want to manipulate it and do something really quick with it at the C level. And Python makes that very easy to do, basically. You'd never be, the main motivation for ever touching Python is that lets you do things really, really quickly, the same speed as C, no matter what it is, in theory. C can be really hard to figure out how to do things quickly, of course. And then the other thing, which is also illustrated here, is you can call functions that are defined or that are available to C just directly like this. Notice I'm calling sign. Directly. So if you find some big C or C++ library, and there are an absolutely ridiculously large number of extremely powerful and important libraries in C and C++, you can directly, with absolutely zero overhead, call them from Python. And that gives you the potential of doing very fast stuff without having to write a bunch of really subtle conversion code to go back and forth, since it's done automatically. Yes?
And that's all the code I had to see that.
Yep. Yeah. I mean, there's a whole manual for using Python, and it's complicated. And probably, I think like 200,000 or 300,000 lines of the Sage library itself is written using Python at this point, maybe more. So, we used it an enormous amount all over the place, and there's a lot of, and we're not the only ones that use it. It's used by lots and lots of other projects, so it's got polished quite a bit over the last 9 years. And there's also repeatedly been like other projects that pop up that try to make Python fast, and they don't have like the same depth and polish as Python. In that Python, like it could just solve, it may be a little harder and you may have to know C, but it will solve your problem as far as making things fast. Okay. Okay, let's look at the next thing, which is, so on Monday I just threw out a little question for this kind of random example I made up, which is there a simple formula for the sum of sine of m, where m goes from 1 up through n? Just like there's a formula for the sum of the first n. Wow, that's actually wrong. That should be nn plus 1 over, that less than or equal should be less than. I don't know why I did that. I'm just going to change it to less than. So there's a formula for the sum of the first n integers. It's if you learn induction, it's like one of the first exercises you'll do, which is to prove that you have this formula. Okay. So the question is there a similar one for sine? And it's not obvious to me whether or not there is one, but in Sage there's a sum command. Remember you guys asked, is sum in Sage the same as sum in Python? The sum function in Python just takes an iterable and adds up all the things that you get from that iterable, like adds up all the elements of the list. In contrast, the sum function in Sage, it will do that if it can't do something else, but it also has a couple of other ways of being called. For example, you can give it a symbolic function like this as the first input, and then some other parameters. This means the symbolic sum of sine of k, where k goes from 1 to n. And it turns out that Sage, really Maxima in this case, knows how to simplify this sum. It has a rule that does that, and you end up with this formula right here. And notice there's no big sum here at all. It's just this formula. For any value of n at all, it's this formula. And so evaluating this is going to be very fast, even if the input is 10,000 or 100,000, right? So let's try this out. So there it is. Actually, just for fun, let me do one more similar thing. So if you do sum just of k, See, it finds that formula that I mentioned before. Do it like that. And if you, I don't know, maybe you want to know what the sum of the squares are up to n. And there it is. So lots and lots of these sort of sums are available. This is the sort of thing that computer algebra systems are good at, which is encoding this sort of problem. Okay, so let's take this one right here and evaluate it. Let's see how long it takes. So I'm just substituting n equals 10,000. This is the evaluation that we started with it taking about 4 to 5 seconds. And then we got it down to 2 milliseconds by using math.sine. And we got it down to about this speed in this particular instance using Python. But of course, if you put in a much larger number, you're going to get the same speed pretty much. It's not even going to depend on the input. So it's much better in the limit. So it just sort of, it's like replacing an it is replacing an O of n algorithm by an O of 1 algorithm. So it's dramatically better. But there's just, in terms of complexity, this won't speed it up at all, but there's another thing called fast float. This is really cool. I think this warning goes away if I do fast float like this. We just used to have to do it that way. Nope. Why does it do that? Doesn't matter. It's a deprecation warning. But what this does is it takes us. Actually, I think I just have to give the variables. So I think I have to look at the help. The deprecation warning is kind of annoying. Vars. Okay, so now I don't have the deprecation warning. So f again is this big thing at the top. Now let's say you want to evaluate it a lot, and you're excited that it's a lot faster than that big sum, but maybe it's still kind of annoyingly slow evaluating this lot. You might think, oh, I could rewrite it in Python and make it fast. But do you really want to do that? You'll end up having to write a whole bunch of code that involves the math.h and evaluating some of these constants and numbers, and you'll end up with a big mess that looks nothing like this. And that's kind of annoying, right? And you just feel like you're doing something mindless. So you don't want to do that. And you're not going to, you'll have to look up what is arctan called in the C standard library. Maybe it's atan, maybe it isn't, who knows? What are the subtleties? So let's avoid doing that. There's another thing called fast float. What it does is it takes any symbolic expression, like that one, and it compiles it into an internal form that can be evaluated very, very quickly. And then it gives you back something that you can then call. So let's take the result and call it. It's a lot faster. The one above, well, the speed up is a factor of, looks like, almost 400. So okay, it isn't 500, but it's very, very fast. See, that's 827 nanoseconds per call. So let's just think about what happened. Our first naive program to compute the sum of the sines took about 5 seconds when given input 10,000. We're computing the same thing right now, and it takes less than 1 millisecond. It's taking 827 nanoseconds to do. It's giving us the same number. Doing it using a different algorithm, and then B, evaluating this big expression more efficiently by compiling it to some internal form. But at the end of the day, and I really hope this is the case, if you actually look at the number you get, it should be the same. 1 point, does that look right? I have no idea. I've never actually looked at the output. Is it supposed to be 1.6? I don't know if anyone looked at the output ever. Whoa, that is different. Wait, could be off by 1. Oh, okay, it is different. But I think the reason is, look, I'm summing up to n here rather than n minus 1. So let's see what happens if we change this. Okay, and then do this again. And then do the fast float version. Now I really hope we get something that's about 1.9. Yes, okay. So in coming up with this O of 1 algorithm, this big formula, I was off by 1, and the answer was in fact wrong. I was summing all the way up to including n rather than n minus 1. So be careful. But the speed is the same. Okay, so you have a question.
Yeah, how does Sage get that close form, like an arbitrary constant?
So in this particular case, it calls a package that's written in Maxima. So there's the first computer algebra system, which was written in the 60s, is called Maxima, and it's written in Lisp, and it got developed over a long time, since before anyone here was born. And this guy, I think, it got open sourced in the 90s, and hence it's still alive. And there's a chunk of code in it that's either written in Lisp or in the Maxima language, I don't know because I've never looked at it, that takes formal sums and simplifies them. So it has a whole bunch of rules and it recognizes patterns and so on. How it does that, I've never looked at the code. I didn't write the relevant wrapping either. So Sage, by the way Sage calls Maxima is that there's something called ECL, Embedded Common Lisp. It's a way of embedding a Lisp interpreter into a running C program, and Sage uses Cython to directly call Embedded Common Lisp's running version of Maxima. So you run Maxima and Embedded Common Lisp and call it all at the C level, which is interesting in and of itself. So that when you call code written in Maxima, it's extremely robust and fast to do so. In other words, I'm not answering your question, but I don't know, actually. I mean, honestly, I had no idea whether or not there was a closed form formula for this. Okay, by the way, if you just plot this, it looks a lot like, here's a plot up to, these are the partial sums. So this thing behaves very nicely and regularly, which would give you a hint that there's probably a nice formula for it. Okay, the last thing I want to show you is very short, and then you'll do stuff. This is the question that Doug Lind asked. He wanted to compute the area using double quad. This is a function in scipy.integrate, which does like double integrals numerically. So scipy is a Python library for numerical computing, similar to MATLAB kind of, but for Python. And it has lots of algorithms where it takes like a Python function, something you can call in Python, and then does stuff. And many of the algorithms are wrappings of very polished Fortran and C code that's been developed over many, many years. So what Doug sent me was basically this one line of code which takes as input a Python function, something you can call with two inputs. I didn't mention, by the way, this lambda notation. It's very similar to writing def f of xy colon and then having a block, except you can only have it on one line. You say lambda, and then you give the input variables, and then an expression that gets evaluated, and the result of the function is that. So it's like a function with no name in Python. It's the only way of making a function that you don't name in Python, which is very different than many other programming languages. Like in JavaScript, you just say function and give inputs, and you can make functions with no names all over the place really easily. It's extremely common to do. Whereas in Python, there's a very crippled way of making functions with no names. And that's what this is. So I'm just explaining what that is. So here's the calculation he was doing, and if you time it, you'll find that it takes about a second. And so I was wondering, I wonder if I can make it faster than a second. And I don't know a priori whether I could or not, but given these sort of cosines, we could have used various tricks like math.cosine instead, math.log, etc. But I'll use fast floats, which will take what's inside of here and then make some thing that you can call that can be evaluated very, very quickly. Okay? And so here's the original code, about a second, and then here's how long it takes using fast float. All I did was the following. First, I made a Sage symbolic expression, and then I called fast float on it, and then I got something super fast. It's really kind of ironic because so on the first day when we talked about that sum, the reason it was so slow is because sine of 1 plus sine of 2 plus sine of 3 was all sort of kept symbolically and not simplified. They weren't all turned into floating point numbers as you go. But exactly that ability of Sage to represent these arbitrary symbolic expressions lets you easily define functions that you can then make really fast if you know about fast float. So that's what we're doing here. So I just make a cheat. It works just like f. You can call it. There's like a little bit of overhead in this one line, but once you've done it, you can then call it many, many times. So you can see that it's extremely fast. And so actually just comparing them using time it. So percent time, that runs the code exactly once and tells you how long it took. If it took 0.00 seconds, you need to do something better, so you time it. You can see that it's there's a huge difference here. So the original one is 780 milliseconds each time. The new one is 1.34 milliseconds, so it's over 500 times faster using fast float, which is great. So we have only 4 minutes left, but I want you to at least try something. So I made a little thing where you can put whatever symbolic function you want in here, and then do fast float on it, and then also just make a Python function that has nothing to do with symbolics or whatever, and but it's the same one. And then you can try timing yours versus fast float versus whatever, and see how much faster it is. Okay? So you can try this one or make up something yourself. X times y, x to the 10th plus y times cosine of whatever. Okay, so try doing something there. And then I'll walk around and make sure that you're figuring it out. Okay? Anything you want. You absolutely cosine of x squared, cosine of cosine of cosine of x. Whatever you want. Factorial of x. Gamma of x. You can just type factorial. Yeah. I have no idea if this is going to be before. I think you can say factorial. It might not be fast. If that doesn't work, you can say gamma. At least. Gamma of x is x minus 1 factorial. Okay.
What does fast float do exactly?
It takes a symbolic expression, which I'll talk about a lot more when we do symbolic calculus stuff, just tubes, and it compiles it into an internal call stack that it can evaluate very quickly. And it has for a whole bunch of different special functions, not so special functions, like little bits of code that will evaluate them. It itself is written in Python, but it doesn't actually compile like to machine code. It's still all done in the local Python program. The code is, you can do double question mark and stuff like that. The code. There's some file that, right after password. There's a file in Sage that has the relevant source. I think you need to put the double question mark right after password. Otherwise you're getting just do tab. Put the cursor right here, right after the double question mark, and do tab. Tell you about the password function. Question? Oh, so that makes the number 20 but as a floating point number. And the reason for doing that in benchmark is to avoid overhead in turning 20 into a floating point number, since I didn't want that to be part of the benchmark. So I just wanted to do that outside of the loop. Because it would be a little unfair if I had to convert 20 to a float. I just wanted to do it ahead. So what that does is it makes a floating point number 20. It makes a Python floating point number. I don't know why that would happen, but it did. Copy and pasting that. Because it just created one step. But it wasn't. Maybe some sort of reason.
No, are you going to,
There's something timed out. Tried to put it starting out with some way too
Carson's brother's problem. Yeah. Got a balance then?
So, I guess that one's
Next. Good luck, Warren. Take care.
Okay, well, it's good that I know about
And run one column is
Oh.
so this is
Oh, interesting. It's the same problem.
Same
Maybe
problem.
It's literally the same problem.
yeah.
We just go backwards. Now in this case, I'm not sure if I actually saved. So I pushed out today's stuff like a minute before class, and it did say it timed out, but I think maybe I just didn't save this file. No, it's saved here. It's definitely that's the right size there. Let me try looking at it in another person's directory. Oh, it's fine there. That's weird. All right, let me try resending it to you to see what happens. Sign again. That's really weird. It's just not. It's just empty still. Why is that? I'm gonna try just deleting it and then recopying. Now it's fine. So it wouldn't. Well, there it is. I want to look at whether your project's been running for a long time. Because there were a bunch of fixes that I pushed out, but I didn't force all projects to update.